All right, today, people, we're gonna cover 3 sections in one video. I'm not gonna be here this week, so I'm gonna teach you, what chapter is this? 17.1, 17.2, and 17.3. Chalk. What is he doing? Okay, the title of this chapter is called Gradients, Joe. Okay, so I'm going to show you a theorem. Those of you following along in your book, we're on page 695. It says, if f has continuous first partials in a neighborhood of x, then f is differentiable at x. And this is the symbol for gradient. So if you have a function, can be of 2, 3, or whatever variables, this symbol here means the gradient of that function. Okay? So to compute it, all you gotta do is, well, they write it in IJK notation. I just rather write it like this. So the partial with respect to x, the partial with respect to y, and then the partial with respect to z. Now we already know how to compute partials, right? Yeah. So I'm just going to teach you the thing. If you want to read the proof, you can. It's just basically the definition of the derivative. And then I'll do some examples. So this first section is so easy. All you have to do is compute the gradient.
This part.
Yeah.
What does it mean by the neighborhood of x?
Nearby.
Nearby?
Yeah.
Like, what do you mean?
In the neighborhood. Close by. In the vicinity.
Like a point?
Well, like you have a 3-dimensional surface, yeah?
Okay.
And then, I don't know how you draw it, so like if you have like a surface like that, like at this point, if you're in the neighborhood,
So it's just
What are
anywhere.
you out
Nearby.
of the
huh?
Like, when are you out of the
Yeah, whenever.
I don't know.
So,
What
so,
do you mean?
It's just like
okay, so whenever this problem shows, I'll just assume that. It's
you don't need to worry about that.
Okay.
So here's an example in the book. You have a function of x and y. This is 2 variables, yeah? X e to the y minus y e to the x. I'll just do the examples for you. Compute the gradient. Okay? So all you have to do to find the x component of the gradient is a vector now. You take the partial with respect to x. What is the partial with respect to x here?
EY.
E to the y.
Oh, sorry. E to the y minus y e to the x.
Okay. And then part, what is the partial with respect to y?
X, E, Y,
Why do you guys say that? It's e to the y.
minus E, the X.
Yep, there you go. That's all you have to do tonight. It's so simple. So that's the example they have. They write it with the IJ notation. I rather write it like that. Okay, and then, I don't have to scroll. Second example. Now we have a function of 3 variables, like this, which is sine of x, y squared, z cubed. Compute the gradient. Okay, so partial with respect to x, Cho. X component of the gradient.
Cosine Y squared Z cubed.
No.
No.
The derivative of sine box is cosine box times the derivative of box with respect to x, which is
Oh, Y squared X cubed, or Z cubed.
y squared z cubed. Okay, the y component of the partial.
Cosine that whole thing. And then 2y x z cubed.
2x
Y.
y z cubed. That is correct. And then the z component of the gradient will be cosine box times the derivative of box part
Z?
with respect to z.
3xy squared Z squared.
3x
Y squared.
y squared
Z squared.
z squared. That is correct. See how easy this is? So this first homework is easy. all you're doing is computing gradient. Oh, by the way, nobody's gonna ask like what a gradient is.
No.
Huh?
Oh, why is it brown?
It's the vector.
Yeah, it's a vector, but in terms of a graph, okay, let's say you have a surface. Oh, by the way, I looked on my iPad and I forgot I bought like the
Oh my god.
Pocket Cast Premium, so I can graph three-dimensional functions.
Do you have it right now?
Yeah, it's on my iPad.
Oh, right.
So you can just punch in the graph like z equals whatever, boom, and then you can actually grab it and then like view it from different angles.
Wow.
Anyway, let's say you have a surface like this, a gradient at a point, so at a single point, so you see like in 2 dimensions, let's go back to 2 dimensions. When you're in 2 dimensions, like if you have a graph, when you compute the derivative, aren't you computing the slope of the tangent line? Yeah, but see, slope is a 2-dimensional concept. In 3 dimensions, what is slope? We don't have slope, we have what gradient is. So you can kind of think of it as the perpendicular vector of the tangent plane. See, like in 2 dimensions, you have a tangent line, right?
Yeah.
But in 3 dimensions, you can have a tangent plane, like right at this point. This plane is like tangent to the surface. The gradient is the vector that's perpendicular to this tangent plane. So it's kind of like slope, right? Remember when we did 3 dimensions in PCH? Of course not. Because remember, what do you need to write an equation of a plane? You need a point and a perpendicular vector like that. Perpendicular vector. Call that n for a normal vector. So the gradient is this vector that's perpendicular to the tangent plane. That's what a gradient is. It's like a multi-dimensional concept of slope.
Is there a proof to that?
Well, you mean for that?
Yeah.
I don't know. That's not a proof. That's like an application of it. I don't think there's a proof. And then of course you can evaluate the gradient at different values of whatever points. That's just plugging in numbers. I'm gonna let you do that. Okay, so look how fast we got through section 17.1. 17.2, properties of gradients. Now, those of you following along, turn to page 699. Now look at these properties of gradients. Gradient is pretty much like a derivative. That's what it is, right? It's just a vector made up of the partials, yeah? So, on 699, look at 17.2.1 in the box there. Look at this. If you have the gradient of the sum of 2 functions, then all you have to do is take the gradient of each function separately, right? That's just like the one that we had here. I mean, when we took calculus BC. And then the second one, if you have a constant, you can throw the constant on the side like an unwanted pet, just like we normally do. And then when you have a product of 2 functions and you take the gradient, then you got to use what we call the product rule. Doesn't that look like the product rule? Derivative of the first, leave the second one alone. So gradient of the first, leave the second one alone. Then you leave the first one alone, gradient of the second. It's so easy.
That means what you.
No. We're going to do some examples.
No.
Yes.
It's exciting.
Oh, the next concept is directional derivative. Now, I mentioned that to you before, right?
What?
The direction. Okay, here, let me explain. Remember I told you I was driving home one time and I was thinking of like what a partial is?
No, you didn't tell me.
Yes, I did. Here, okay, so suppose you have a curve, like a mountain. Okay, so this is like a,
You did tell us that.
yeah, I know I did. Okay, so this is like a contour plot. So can you imagine that?
Yes.
It's like a mountain. So this is like maybe at sea level, and this is 100 feet, and 200 feet, 300 feet. So here's like the XY axis here, and then, so it's coming up like this. Oh my goodness.
Yep.
Okay, so if you're like standing on the mountain, like right here, and if you look directly to the east, like on the x-axis, the partial with respect to x tells you like I'm standing on the side of the mountain. Okay, I'm on the mountain. I'm hiking up the mountain like this. I'm hiking up the mountain, and then right when I get to that point, I look to the east, which is in the positive x direction. What is the slope of the mountain right there? Just looking this way. Like it could be going up, it could be going down, right? Depending on the what do you call that? The contour of the mountain. Okay? And then if you take the partial with respect to y, it's like this. What happens if you like look this way? Well, since we're going uphill, probably we're gonna look up. It's the slope looking this way, yeah? You know what I'm talking about? But see, so those partials only give you in like the x or the y direction. Is there a way to figure out what the slope is at any direction? Like, what about this direction?
Gradient.
Well, no, it's called the directional derivative.
Oh.
That's what this is. Say, look at this thing. Doesn't this look like the definition of the derivative right there? It says, for any unit vector u, again, do we need to review what a unit vector is? I think we better. Let's say we have a vector that's equal to, let's just do the two-dimensional vector, 3, 4. What is the length of this vector?
5.
5. So this is not a unit vector. A unit vector is a vector of length 1. So how can I get a unit vector that points in the same direction?
5.
Yeah, multiplied by 1/5. So 1/5, 3. There you go, crinkling again. So if the length of this vector is 5, you multiply it by 1/5, now the length is 1. So we call this a unit vector. That's going to be very important in our computation. That's why we learn it. So here it is, theorem 17.2.4. This is on page, what is it, 700? I don't know what it is. I can't see it. Anyway, if f is differentiable at x, then f has a directional derivative at x in every direction, and the derivative, the directional derivative, this is how you write the directional derivative, is equal to the gradient dot u, which is the unit vector.
What is that?
So like for example, you're on the mountain, and let's say you're looking that way. So you're climbing up the mountain, you stop, and then you look over here, you look over there. What is the slope right there? See, it's not parallel to the x-axis or the y-axis, you're looking over there. What is the slope? We need the directional derivative. So the gradient, you guys know what gradient is. A gradient is a vector that's like right there. If you have a tangent plane, the gradient is like a vector that's perpendicular to the tangent plane. Right? That's what a gradient is. And then you have to dot it with u. So here is the direction that you're looking. What you do is you make a unit vector out of it. You make it like have a length of 1, and then you dot it with the gradient. And you guys remember how to compute dot products, right? Or do we need a quick review? Okay,
Wait,
good.
but how would you find that?
They're gonna give it to you. They're gonna tell you so compute the directional derivative in this direction. So they're gonna give you a function first, and then they're gonna give you a direction.
And to find the gradient.
We did that already.
Okay.
You just take the partial with respect to x,
Oh, yeah.
that's the x component, and the partial with respect to y is the y component, and so forth. Okay, let's look at an example. It's just pretty much computational, that's all it is. Oh, there's a nice picture on page 702 on the bottom. Here, it says, namely, the directional derivative is the component of the gradient vector in that direction. In the direction that you're looking. That's what it is, it's the component. Okay, let's do a 2 and then a 3-dimensional one. So first one, this is the same examples in the book if you want to follow along. Actually, it's not a 2-dimensional one. It's a function of 2 variables, so that's like actually 3-dimensional. Yeah? You can think of that as z, that's y, right? So f of x and y, it's a function of x and y equals x squared plus y squared. This is like z. Let's review. What is this graph? This is a quadratic surface, that's why.
Oh,
Wait.
Come on, you had the highest score.
I know, but it just went out of my mind.
Yeah, obviously.
What does it start with? Go.
Parabolic
Cylinder.
cylinder.
No.
Is it parabolic something?
Circular cylinder.
Parabolic cone. Parabolic.
Isn't that a quadratic cone?
Quad.
It's a
not
elliptic paraboloid.
I want to go back to that.
That's like x squared plus y squared equal 4z, right? Except it's just z. It's a paraboloid.
Is that what I said? When I said paraboloid.
You said parabolic. So
Oh, yeah.
Yeah, that's different.
something silly there.
What is a parabola? Is there a parabolic cylinder? There's an elliptic cylinder.
Yeah. there.
Oh my goodness, we're in so much trouble. Okay, so if we attempt to graph, what the heck, let's attempt to graph this for funsies. So it looks like this. When x is 1 and y is 2, what is the z coordinate? 1, 2, what is the z coordinate going to be? 5. So maybe about here. Right at that point, we're going to compute the directional derivative in the direction of 2I minus 3j. Of course, that's the same thing as just 2 comma negative 3, yeah? So which way would that vector point? The x component is 2, but the y component is negative 3. So it's kind of like pointing that way.
Yeah.
Yeah. And then, of course, if you have a tangent plane, the gradient is perpendicular. How do I even draw this? It's perpendicular to this plane. I don't know, like that. That's what the gradient is. You draw the tangent plane, it's the perpendicular vector. So anyway, we want to compute the directional derivative. So how do we do that? We take the gradient and we dot it with a unit vector that points, I guess I should put the vector thing on it, because they're supposed to be vectors, with the unit vector of the direction that you're going, you're looking at, or whatever. Okay, so first let's compute the gradient. We know how to do this. This is what we did last chapter. What is the gradient here? What is the partial with respect to x? 2x. What's the partial with respect to y? That's simple. And then what is u? What is the unit vector that points in this direction? Well, what's the length of that vector?
Root 13.
Root 13. So if the length of this vector is root 13, what can I do to it to make it have a length of 1?
Divide.
Multiply it by 1 over root 13. So 2 over root 13, comma, negative 3 over root 13. So the directional derivative, how did they write it? Like this, I guess, is equal to, you just take the dot product of these two vectors. Oh, but they gave us a point, so it's even easier. I forgot, it says at the point 1, comma 2. Well, of course, it's actually 1, comma 2, comma 5. That's what it is, right?
Yeah.
But they just gave you this, because once you know the x and y coordinates, you just plug it in to get the z coordinate there. So actually, we know that the gradient at this point is what? What happens when I plug in 1 for x? 2. What happens if I plug in 2 for y?
4.
You get 4. So the directional derivative at that point is, how do you compute the dot product of two vectors? What do? You multiply the x components, multiply the x components, 4 over root 13, you multiply the y components, negative 12 over root 13, and you add them.
Negative 8.
Negative 8 over root 13. And now notice that this is a number, yeah? This is a number, and what does this number represent?
The
The component, it's the component of this, of the gradient in the direction of this direction. So the component. So like remember we had that problem on the test once. I said, what is the component of this vector in the direction of this vector? That's exactly what we're doing now. We're finding, oh, that component right there. That's why it's a number. It's a length. It's a component. Yeah.
If this problem didn't give you a point, then would you come up with a finite number?
Okay, if they don't give you an exact point, then I guess you would just leave that. You just take the dot product of these two, so you're gonna have x's and y's in your answer then. So then you can plug in any point you want. Okay, now the second problem is now a function of 3 variables. So actually this is a 4-dimensional graph here. X, cosine y, sine z, at this point, 1 pi, pi over 4, in the direction of 2, negative 1, 4. This is all computational, man. So, first of all, let's compute the gradient. Okay, what is the x component of the gradient, Joe? Select,
Cosine y, sine z.
okay, cosine y, sine z, you mean.
Yeah.
Yeah. Ha, what is the y component of the gradient?
X sine y sine z.
What?
Wait,
Negative.
I left the space.
sorry. Negative.
Yeah, the derivative of cosine y is negative sine y. And then part, what is the z component?
X cosine y cosine z.
Oh, you think you're good, huh?
I am.
Oh.
Okay, and then the unit vector? What is the unit vector? Well, what is the length of this vector right here? The square root of this squared plus that squared plus that squared. Square root of 21? Who makes up these hard numbers? Don't worry, on my test, they can come out nice. Pythagorean fourpole or something. Triple. Forgot, Pythagorean fourpole. Okay, anyway, so, what is the unit vector that points in that direction? 2 over root 21, negative 1 over root 21, and 4 over root 21.
Yeah.
And then, what is the gradient at this particular point, though? So here's the gradient. If I plug in 1 for x, pi for y, and pi over 4 for z, what is the first component? Joe! Plug in 1 for x, pi for y, and pi over 4 for z. Just plug in numbers. Plug in 1 for x is no x. Plug in pi for y,
Negative 1 times.
and then plug in pi over 4 here. Come on, man.
2 over 2.
Root 2 over 2?
Yeah.
Okay. All right, how shall we just go 1 over root 2 then?
Um,
Okay, how? What is the y component?
It's negative root 1.
Oh yeah, negative 1 over root 2. And then how? What is the y component of the gradient at that point?
1 root 2.
You got you got the easy one.
What do you mean?
The sine of pi is 0.
Oh.
Oops. So, and then part with z component at that point?
Negative 1 over root 2.
Negative 1 over root 2. That is correct. So to compute the directional derivative at this point, maybe I should put the point here. That'll be proper mathematics there. It is simply the dot product of these two vectors. So multiply the x components. That's negative 2 over root 42. This is ghastly. Plus 0 minus 4 over root 42. This is negative 6 over root 42. And we probably should simplify that to negative 6 root 42 over 42. But 6 goes into 42 7 times. Negative root 42 over 7. And again, it's a number. It's the component, that's why, of one vector on the other.
Okay.
See how easy that is? Okay, and then now 17.3. Oh, you guys need to read this. A differentiable function f increases most rapidly in the direction of the gradient, and it decreases most rapidly in the opposite direction.
Oh, okay.
So like if you have a surface, it's going to increase most rapidly in the direction of the gradient. But isn't that just common sense? Like right at this point, here's the gradient. Isn't that like the most rapid increase? Because if you do it, like for example, if you're standing on, how you could be standing on that? Okay, let's say the mountain looks like this. Then. You're standing over here, you're hiking up the mountain. So here's the tangent plane, so the gradient is perpendicular to that. So if you're standing there, and you're looking in the direction of the gradient, that's where it's increasing most rapidly, right?
Wait, what's
Because the gradient, no, f increases most rapidly. The function is increasing. Because if you look in a different direction, right? then the component of the gradient, oh, here, maybe I should make it longer. Let's say you look in that direction. The component of the gradient over there is only gonna be this. It's not gonna be as long as this one. Right, it's gonna be shorter.
Okay. Well,
Because isn't, okay, look. There-
Huh?
Why-
I know.
Why do they put these, why is it, the rate of change is then the magnitude of the gradient?
Is it the magnitude or is that the
No,
absolute?
no,
What is it?
no, when you have a vector, the bars mean magnitude.
No, but there's 2 bars though.
Yeah, well, this book does different things, so
So you need
that's the magnitude of the gradient. So the rate of change is simply the magnitude of the gradient. I don't know, let me think about that for a while. Might be a long while. Okay, finally, 17.3.
Oh, listen, I feel like this is gonna be like.
Look how easy these problems are, it's all computational. 17.3, the mean value theorem and the chain rule. Okay, I'll tell you right now, I'm not gonna test you on the mean value theorem.
Oh, thank God.
But doesn't that remind you of the mean value theorem? Remember in 2 dimensions, if you have a if you have a continuous and differentiable function from A to B, there's at least one value of C
Oh.
somewhere between A and B, such that f prime of C equals f of B minus f of A over B minus A. Remember you had to memorize that for the AP exam?
Yes.
Doesn't that remind you? Look at that mean value theorem on page 709. What happens if you divide by the B minus A? That looks exactly like the mean value theorem.
Oh.
But this is for higher dimensions, of course. Okay, this is the one you gotta know, the chain rule. For those of you following on the video, this is on the bottom of page 710. If f is continuously differentiable on an open set, and R is a differentiable curve, then the composition f of R is differentiable and the derivative of f of R is the gradient of f at R of t times R prime of t. Doesn't that remind you of the chain rule?
Yeah.
Yeah, exactly, except this is for higher dimensions. Okay, why don't we do a problem then?
Yes, please.
Okay, here we go. Look at this. This is on page 711 if you're following along in the book. Hopefully you are. So here we're given a function of 2 variables, which means it's 3-dimensional. F of xy is equal to 1/3 x cubed plus y cubed. I wonder what that looks like. You know what? I should graph it and show it to you. Okay, find the rate of change. That means compute the derivative of this curve with respect to t along this curve. R of t equals, I'm going to write it in this form. I don't like the IG notation here. A cosine t, b sine t. By the way, what is this curve right here? This is parametric, remember? A cosine t, b sine t. What is that? Ha! This is a 2-dimensional thingy here. Part?
A circle.
No. Oh! It's an ellipse. This is, okay look, this is like x equals a cosine t. Now is it ringing a bell? Y equals b sine t?
Yes.
So x over a equal cosine t. Y over b equals sine t.
Oh.
Square the equations. Woo, woo.
If it was
Add
17,
x squared over a squared plus y squared over b squared equal 1. That is an ellipse. See, if these 2 numbers were the same, then it would be a circle.
Yeah, I just.
Yeah.
Confused, yeah, right?
Anyway, it's an ellipse.
Okay.
Okay, so compute the rate of change. So if I want to compute here, let's write down the chain rule. The derivative with respect to t of f of r of t, except that's a vector here, these are vectors, is equal to f prime of r of t times r prime of t. That's the chain rule. This is the way we learn the chain rule in 2 dimensions. The derivative of f of g of x is equal to f prime of g of x times g prime of x. Doesn't it look eerily similar? Yeah. Okay, so let's do this. So first we need to compute the gradient of f. What is the gradient of f? Cho, gradient of f.
Wait,
This is the function.
x squared plus y squared.
No, comma y squared.
Oh, y.
Yeah, because you take the
What's your one? Oh,
when you take the, what's the derivative of x cubed? 3x
no.
squared.
Never mind, never mind.
The 3 cancels the 1/3.
I mean, the f derivative is gradient of f?
Yeah, this symbol means gradient.
I don't know, like, you know how you, oh, is that just for the two?
Oh, did I forget to put the gradient sign in?
Yeah.
I did.
Yeah,
Oh.
Oh, there you go.
okay.
Because the gradient is like the derivative. Cho, Cho, what are you doing? Get back in your seat.
I'm trying to look for a math book.
Yeah, when we're finished.
Oh,
Oh, you guys are killing me. I think we can just write it already. Okay, so we took the gradient, and then now we're gonna take the curve and plug it into the gradient. So this is x, this is y, right? It's like parametric equation. So what happens if I take that and plug it in here? What you gonna get? A squared cosine squared t. Okay, that's ugly. Comma, and then take the y and plug it in there. B squared sine squared t. And then we're gonna dot it with the derivative of r. Okay, here's r, which is like you can think of that as position vector, if you want to. So we need to dot it with the velocity vector. What is the velocity vector? Ha,
Yes.
velocity vector.
A.
Yeah.
Negative A.
Okay.
I was gonna say it later. Negative A sine
Okay.
t b cosine.
Okay. Now we dot product them and we get negative a cubed
Sine t cosine squared t.
cosine squared t sine t plus b cubed sine squared t cosine t. And can we do any factoring? That's not gonna help you. This is ugly. Because if you factor out a sine t cosine t, what are you gonna get? Negative a cubed cosine t plus b cubed sine t. Don't worry, when I make a problem, I'll make it come out so it simplifies pretty nicely. Okay, let's see if they have any other good examples. Hey, they did exactly what I did. They factored it out. No, we don't need to do any more, yeah?
Yeah.
Yeah, this is just nonsense. This is easy. This is just computational. All right, and then just to let you know, oh, you know what? Nah, I'm not going to teach you that now. That's enough. But this is what's coming up. We're going to actually write the equation of the tangent plane. And then what comes out, then here's the most interesting part of the chapter. Then we're going to compute maximum and minimum values.
constant parts.
That's going to be fun. It's not as easy as you think, you know.
Oh, really?
Okay, here. I'm just curious what this graph looks like. Does anybody want to take a guess what this graph looks like? We're going to graph it on my,
It's
what is that thing called? Oh, educational things. Oh, you dummy. Hey, where is it? Oh, that's because it's under math. It has its own. Okay. So how can I do a new one? All right, new entry. So we're gonna do a 3D plot, and then you just punch in.
Wait, you bought this?
Yeah, I bought it. It was like $10.
Just work, do you need help plugging it in?
I think you just have to, I don't think you even have to type in the z, so let's just try it. In fact, we don't need to graph the 1/3, yeah? It's just a constant, that's why. So let's just graph x raised to the third plus y raised to the third. What do you mean if I need help? Go. There, here, this is what the surface looks like right here. Can I click on it? No! No, I want to make it, like, can you make it bigger?
Is it a green thing?
Yeah. So here, Joe, sit over here.
No.
No, this is a different graph, but I'm just doing it for fun. So this is what the graph of x cubed plus y cubed looks like. Sit over here. Is there any other Joe here? Oh, you could have just sat there.
You can show it to me for reading.
Okay, and then you can grab it, yeah, and then you can just
Whoa.
look at it from different angles. It's kind of weird looking, huh?
How do I waste the money?
There, that one looks better. There's a nub, there's like a nub there. And then a
Oh, wait, that's
nub
actually
on the
pretty
other
cool.
side. And you can flip
Wait,
it
no,
over.
there's a point. There's a random.
No, I don't think, you mean the thing hanging on, no, I think that's just the way it graphs. And what's the equation of this one? Sine x plus cosine y.
Oh, these are cool.
Ooh.
Oh, I know how you can expand.
How come some of them have?
Oh!
What?
Well, how did you know that?
Good.
There.
Can you make this bigger?
No, that's a big easy.
Wait.
How come the other one had different colors and this one's like green?
You can, that just changed the scaling.
Yeah.
Here, let me just show it to the video. Can you guys see this?
No one watches it.
What?
Josh.
I don't know if you can see this, but look.
You see?
You can grab the graph. This is z equal x cubed plus y cubed, and you can rotate it. Who knows? Rotate it around. Oh. This is pretty neat.
It's fucking so cheap.
Okay, whatever. Just
Wait,
turn off
can
this
you-
video already.
Can you graph x cubed plus y cubed plus z cubed?
No, that would be a 4-dimensional graph then. No can.
Or like x cubed plus y cubed plus z cubed equals 1?